Okay, so the first problem we're going to be looking at here is going to be problem 238. And we want to set this up and kind of get you started so that you can, continue to finish this up. So this is one of your application problems for Module 3 that you will be handing in. So the illustration is up here, okay? And it says two forces, P and Q, are applied as shown to the bracket in the spacecraft frame. Knowing that the connection is in equilibrium, okay, that means that we can use those two equations of equilibrium, some of the forces in the x equals 0, some of the forces in the y equals 0, and that P is equal to 600 pounds going down there, and Q is 800 pounds going up and to the left at 30 degrees from horizontal. We want to find or determine the tensions in cables B and A. Okay. Now, as you can see here, naturally, we see a point where they all would intersect. That means that they are a concurrent force system. And right where that intersection is, that's where we're going to set up our X and Y axis. Okay. All right. So here again, nice big diagram at the start of our problem. So I'm going to kind of zoom out here a little bit. And this is application problem 2.38. And right at the top, so I don't forget, I want to put my convention. Everything going to the right and up is positive so that I don't forget to do that. That's very important. And then I'm going to draw my X and my Y axis. Okay, again, taking up half the page, nice and big. And then I'm going to draw each one of these forces as I see it. Now for P and Q, I don't think I'm going to say P is equal to. I'm just going to put for P 600 pounds. For Q, same thing, 800 pounds, because I have the information. Why add extra stuff, right? So I'm going to put P going straight down here. This is 600. Make sure you put your units. And then Q is at a 30-degree angle from horizontal. See, 30 degrees, not 300. And that is 800 pounds. There we go. And then we've got A. And we've got B, which is horizontal going to the right. There we go. All right. Now, our next step is going to be components, right? Diagram first with convention, show everything in place, and our next step is going to be components. So I'm going to put that down here. But before I do, I need to draw them on my axis system. So go ahead and draw the components for any of the forces that are not currently lying on the X and Y axis. Okay. Oh, I guess I do have to, I'll call this QX. So I will say Q is equal to, yeah. I needed it for the X and Y components. So I could call them QX and QY. So you should have an AX and AY and a QX and a QY, all lying on the X and Y axes. Remember, we're not floating any components. Okay. And once we have those in place, we can now go ahead and calculate and determine our components. Did you guys want to go through and get the components, or do you feel comfortable with that? Who would like to calculate the components together? Deb says sure. Okay, we're doing it. We might as well do it here. Yep, we're here. So let's go ahead and do AX and AY. I'm going to do mine down here. You can do yours independently over on the side, okay? And then we can compare. It's funny how many times I do cosine of 60, cosine of 30. I should have those in my head, but I don't trust myself. So I always calculate them. Now, because we don't know the magnitude of A, each one of those components is going to be in terms of that hypotenuse. So they have A in them, and that's as far as we can go. That'll be a variable that we're going to solve for when we do our equations of equilibrium. And then once you have AX and AY, then go ahead and calculate the magnitudes of QX and QY. Now, because we have Q equal to 800 pounds, we now can get magnitudes for each one of our components for Q. Yeah. These two steps have been consistent for each one of the problems that we've done, right? Diagram first, break it into X and Y components where necessary, and then calculate those components. Now, once we have our components, what's the next step that we're going to do? Yes, equations of equilibrium, right? Okay. And what are those two equations of equilibrium? Anyone? Chris knows. He's smiling. He's like, I know. Sum of the forces in the X equals 0, right? Yep. Sum the forces in the X equals 0. You have to write it out in this format. You have to put the summation symbol in front. Capital F sub X is equal to 0. And what's our other equation? Oh, thank you, Matthew. Yep, Deborah, sum the forces in the Y equals 0. Okay, and thank you again, Matthew. Excellent. Now, I am going to let you go from here, okay? So remember, as you write your variables down below, you're going to look back up at your diagram, and these, in that first line underneath the sum of the forces in the X, you're going to look at just that X axis, and you're going to write the variables based on the convention that we created up in the upper right-hand corner, okay? And then set that equal to 0, then put any numbers in, and then solve and combine as you're able. Then you're going to do the same thing for the y-axis. You're going to take the variables that are on the y-axis here, that's writing it in its variable form first, then putting any numbers in place, and then some combining and solving as needed, okay? If you end up with two equations with the same two unknowns, not to worry, use substitution method. But sometimes that'll be the case, and sometimes you might be able to work it out between these two equations, okay? So that's a good setup for 238. Any questions as you're looking here? Okay, so then you'll be ready to finish that one up. Then we've got number 244 is the next problem, or the last problem that you have for application problems in module 3. So let's take a peek at what that one looks like. Okay, 244. So for this one, it says for the cables in problem 236. Okay, problem 236. So that means we've got to go back. And I think that one sounds familiar. I think we have 236 as one of the problems that we're doing. Okay, so here's the illustration for 236. And this problem says, for the cables in problem 236, it is known that the maximum allowable tension is 600 newtons in cable AC and 750 in BC. Okay. So AC is right here. BC is right here. So they're giving us the values along those cables. Okay, so along that cable for A, we are going to have 600 newtons pulling away, and we are going to have 750 pulling away. All right, we'll see that in just a little bit. In both, let me see here, determine the maximum force P. P is the one that's pulling down and going to the left, okay? The maximum force P that can be applied at C, and the corresponding value of alpha, okay? And the corresponding value of alpha. So good. All right. So let's see how we're going to approach this one, because this one is a little bit different than what we've been, than what we've been looking at. What happened here? There we go. Okay. So first of all, let's draw our free body diagram. Okay. Let's draw our free body diagram. Free body diagram at the top here is going to be half of our page. So nice big X and Y axis. Again, we've got labels, we've got angles, we've got arrowheads. Okay. We want to make sure we add our convention so we don't forget about that, because that's like minus, I think I take off 12 points of the 10 points. No, at least 2. I will say that, at least 2 points if you forget it. So yeah, it's one of those things. If you forget it, so you get the points off, you rehand in, no big deal, then you won't forget it anymore. Sometimes mistakes are our friends. All right. Do you ever notice that though? Truly. Sometimes you make a mistake and then like you lock your keys in your car. You ever lock your keys in your car? We all have, right? And then all of a sudden the next time, and probably for the next 25 years, before you get out of your car, you're like, okay, where are my keys? So it's a good thing. It's a good thing. It's an inconvenience at the moment. All right. So our first one here, this is going to be our BC going up and to the right. And remember, I'm going to call this B is equal to 750 newtons, just because B is that variable that it goes to. And this is at a 25-degree angle. Okay. And then we've got at a 45-degree angle, we've got 600 newtons going up to point A. So we'll say A is equal to 600 newtons. And this is 45 degrees. So these were the two values they gave us in the problem. Okay. in the problem. This is good. That's good. And then we've got P, right? We've got P going down and to the left. We'll show it something like that. And it's just that value. And then you're going to notice we're going to put the angle here, and we're going to call that theta. Okay? Theta. Okay? So that's our diagram, step number 1 in our convention. Step number 2, we know is going to be components always, right? So that means we need to go back up here and draw our components in place and label them. So go ahead and do that for each one of the forces here. So once we have those all drawn, we can now find the magnitudes of the components AX, AY, BX, BY. So go ahead and do that. All right, go ahead and find those values. Uh, Now just do the components here for AX, or I mean for forces A and B. Don't worry about PX and PY yet. Okay. So these should be the final answers. So you will have magnitudes for these because we know the hypotenuses for each one. And the reason we don't have to do P here is because we don't know what theta is. We would have the cosine of theta, and there's nothing to put there, right? So we'll wait on that. Okay, wait on that. All right. So our third step then is going to be our equations of equilibrium. Okay, equations of equilibrium. Okay. Now, here's where I'm not going to solve anymore. I'm just going to kind of point you in the right direction. So I'm going to ask for everybody's attention right now. All right. So that don't be trying to finish this up. Okay. Just find out what our next steps are here. So equations of equilibrium are going to be sum the forces in the X equals 0. So you're going to go back up here and you're going to look at what is on the X axis. Okay. And this time you will include PX. You will include PX. You will be able to solve for PX. It'll be the magnitude, okay? That'll be your only unknown in that equation. Then you're going to do the very same thing for sum the forces in the Y. And you will then solve for, oopsie, not BY, PY. Okay, because if we look back up here, we look at only our y-axis, and we know the magnitude of AY, we know the magnitude of BY. Our only unknown will be PY. So we'll have a PX and we'll have a PY. All right. Then to solve for P, if you have PX and PY, all right, your step number 4 is going to be find the resultant. Or find the resultant P from PX and PY. And you did that in module 2. That's it. Okay. So those are the steps to finish. Oopsie, I'm sorry for those who are virtual. Resultant. So find resultant of P. You know how to do that. That's a module 2 thing. You have the 2 components. You're gonna find the resultant. Okay. And that would be finishing up the last problem in the application problems. Okay. So once you have all of those done, let's go back to our application problems. Here. So we went ahead the last time we were together, we have the setups for the first 3. This time we did the setups for the last 2. Okay, so you've got good stuff to go on to finish those up. And once you have those all done, then you can hand these in for your application problems. The rest of the time that we have together is going to be lab. So you can, work on these or anything else that you have going on. And then Friday will be independent work time as well, virtually at our normal time. Okay. So that's all that I have for today. Are there any questions? All right. Then I'm going to stop our recording